All right, starting module 90, which is about convexity, we have two big questions that we've developed from previous modules. One is, when should we be worried about getting trapped in a local min that isn't the global min? The other one is the second derivative test from Calc 3. What's the theory behind that? Here's a quick outline, but we'll just see each thing as we go. We did a pre-lab in our synchronous session where we had this problem, producing cars at two factories, and we have not a per car cost, but a total cost at this factory, total cost at that factory for given production levels. And what should we do? And we formulated that in Solver and tried it starting at 0, 0. We tried it starting at like equal number of cars at each factory and saw what the optimal solution was. Tried starting it all at one factory, none at the other, and vice versa. So go try all that now if you get a chance. One thing we had to do to protect Solver from getting square roots of negative numbers is we had to say square root of absolute value of that thing and square root of absolute value of that. It's not a mathematical thing, it's just a protecting Solver from itself kind of thing. So in that we saw that the values you started with could affect what values you ended up with, and you could get stuck in a local optimum that wasn't the global optimum. And the optimal solution initially was make everything at B and nothing at A, but then when we increased the 1.9 so it was larger than the 2, and we saw that the optimal solution was still make everything at B and nothing at A. And eventually when we increased this coefficient enough, then the optimal solution was make everything at A and nothing at B, but we never saw a point where we wanted to make a mix of things like some at A and some at B. So that was kind of interesting. Then we did another problem called electric power generation. By the way, these aren't meant to be super realistic, but they are vaguely realistic in like economies of scale or diseconomies of scale and stuff. So it was a very similar problem setup, but now the total cost is 3x squared at generator A and 2y squared at generator B. So go ahead and formulate that in Excel. We need a total of 4 gigawatts this hour, and see what you get. So what we saw was that we got the same optimal solution regardless of what values we started with for x and y. We never got stuck in a local min that wasn't a global min as far as we could tell. And you might say, well, this generator is just cheaper than that one. Let's just use all generator B and no generator A. But that's not actually what the optimal solution ended up being. It was a mix of the two. And I'm not saying that that will always happen for problems with this kind of cost structure, or in the larger sense that we'll see later. But it is interesting that that it can happen, and that our intuition about what was cheaper was not actually what ended up being the right thing. So we're retraining our intuition. So that was our pre-lab, and now we're going to go talk about some fun stuff in the next video about second order conditions.